So Happy New Year. And it's nice to see that most of you are here after celebrating last night. It shows a really true commitment to the course. So today we have two topics on the menu. We're going to speak about object-oriented programming and about some advanced Pandas capabilities like merging and aggregating data frame and grouping and stuff like that. So let's begin with the object-oriented programming. So it's also sometimes called OOP, which is an acronym we're going to encounter quite a lot in the domain of programming. Now, I should say up front that this is a very deep topic and a very important conceptual thing that, for example, computer science students will spend whole courses dedicated just to this topic. And we're going to have a quite technical and superficial view of this. So we're mostly going to focus on the technicalities, mostly to understand how Python works under the hood. But I do encourage you, if you want at some point to improve your programming skills and being able to write cleaner and more robust code, then I really think it's one of the most promising avenues to improve programming. And I encourage you to look at many resources that there are. So you can also take courses at the university, or online courses, or YouTube videos, or blog posts. So there are many resources discussing this in much more depth than we're going to cover today. Now, what object-oriented is, it's a little tricky to define what exactly it is, but you can think about it as some kind of a conceptual framework for many programming languages. Now, historically, when people started creating those programming languages, the first ones to come about were not object-oriented. So it's only a later development, only a few decades into this whole concept of programming languages. Only then did people invent this concept of object-oriented, which really made, in many ways, programming much more easy and intuitive. So it's a way of thinking about programming in terms that are much more intuitive to us humans. We think in terms of objects and types and classes and members and methods, which are, we're going to explain what these concepts actually mean. And by making it much more intuitive to us, it creates code that is much more clean and much easier to maintain and to extend and to work with. So that's like the motivation and rationale to do OOP. OK, so let's begin with clarifying a little bit of terms. So let's begin with asking what exactly is an object. Now, like I said, it's a bit tricky to define. I don't think I have a very good definition, but I think that through examples, it becomes very clear what we mean. So not very good definition, a circular definition would be that an object is an instance of a class, where a class is the type of the object. So we've seen that in Python we have different types. For example, we have the str type, which stands for strings. And for each type, we can create objects with this type. So for example, for the str type, we can create an object of string, which is, in this example, hello world, which would be then an instance of str. So even though I didn't give a very clear definition, I think it's quite intuitive, and all of you understand what I mean. So each instance of a certain type is called an object. And like I said many times throughout the course, in Python, everything is in fact an object. And the thing that's important to understand about objects is that they have certain properties. For example, they have certain variables which are associated with each object, with the exact instance of the object. These are sometimes called members or fields. So for example, if we have a df variable, which is a data frame, then we saw that we can do df.values. And values is a variable associated with a specific instance that would give us the underlying NumPy values of this data frame. So that's a member of the df objects. And likewise, we have what we called bound methods or bound functions, which, unlike global functions, are functions associated, again, with a specific type and they have access to the specific members and state of the object. So for example, we saw that for a DF data frame, we can call the sort values function. And then we have the data frame sorted by values. And that function is again, it's associated with a specific instance that we have. So if we have two data frames, df1 and df2, and we do df1 sort values, it will give us one thing, and df2 dot sort values will give us a different thing. And same goes for the members and fields, okay? So it's not global variables that we define, for example, in the global environment. These are variables which are specifically associated with a concrete instance of an object that we work with. Okay, so that's an important concept to understand. And really, I think one of the most clear hallmarks of OOP is the syntax that we see very often. So if you go to a programming language that you do not know, in virtually all programming languages which are OOP, you have pretty much the same syntax. You have some objects, dot some function, and then you can call some arguments. So if you see that, you know that you are in the presence of an object-oriented programming languages because you can do something to an object. In a non-OOP language, it would probably render as something like do something, which has to be a global function, and then to that you would have to feed in your objects just like any other arguments. So logically, these two things are the same. So you don't really need objects in order for it to work. You can just create global functions and give them all the arguments that they need. But conceptually, it makes things a lot more clear. And also from a syntax perspective, I think it's very often more readable this way. And this becomes, I think, especially apparent when you start chaining operations, like in this example. So if you see something like object.f1, and then you call on that f2 and f3, it's pretty clear what's going on. You see that you start with some object, and then you call some function on that. And then on this result, whatever type it is, you call a second function with maybe some arguments. And then on that result, again, whatever type it is, you can call a third function. And it's pretty clear like the direction and how these operations work together. Whereas in a non-OOP language, it would probably render something much less readable with very nested parentheses, which is much harder to follow through. So that's really, I think, one of the advantages of working in OOP, but of course not the only one. So let's speak specifically about object-oriented programming in Python. So like we said, Python, like virtually all modern programming languages, is fully object-oriented, even to a larger extent than many other contemporary programming languages. So in many programming languages, even though they are OOP, we still have what's called native types, which are types which are not exactly objects. So most of the time, it will be the very simple types, like integers and floats and booleans. But in Python, that's not the case. In Python, everything is an object, including the simple types like integers and floats, and even functions themselves and types. Everything is an object in Python, like we said many times. And we're now going to see today how to work with classes, and I hope it will give you some motivation to why that might be useful. And most importantly, I hope that it will clarify and give you a better sense of how things really work in Python. And we're going to see that it's really not that difficult. So writing our own custom classes and types is actually very easy and straightforward. OK? OK. So let's see how the syntax actually looks like. So I open the OOP notebook. Is it large enough? Can everybody see? OK. OK, so if I want to write a new class, actually it's very simple. So that's what the syntax looks like. I use the class statement to say that I want to write a new class, and then followed by the name of the class I want to write. Pretty much like we define functions. And then I use this column because I want to start a new block of the class, but in this case it will be empty. I don't want this class to do anything yet, so I just write pass. And that's pretty much it. I define a new type, which is called my class. And then I can instantiate any instances of this class just using simple parentheses. So I create a type like I'm calling a functions. And here I have an A object, which will be an instance of my class. And you see that if I print A or print the type of A, then Python lets me know that it's something of type my class. Now, like we said, objects can have members. So they can have variables associated with a specific instance. So now that I have the object A, I can assign to it two members. One I call member 1, and I put it to be some integer. And member 2, I put it to be some string. And then it's stored like any variable, only that these two variables are bound to this specific instance, like you see here. OK, now.
Bound to the type, right? Not to A.
No, it's bound specifically to A. So if I now create a different, instance of the type, and try to print member 1, then it tells me I don't know what you're talking about. Attribute error. My class object has no attribute member 1. OK, so it's bound specifically to the instance, not to the class. Now, what I do here is non-standard, and that's actually not the way people work with objects like at all, and it's not recommended to work like this. So in real life, when you work with new types, then you should keep some consistency about what members it has, and each class has its own members. And it would be very strange if some instances would have one set of members and the different instances would have a different set of members. So that's not recommended at all to do that, but that's actually the way things work in Python. Okay. So I do it only for illustration purposes. Okay. Now, but here is the main kicker. When we create our classes, we can actually create functions which are bound to these classes. So what we said, like these bound functions or bound methods, as they are sometimes called. And here you can see an example of that. So now that we have the my class type, within it we can create two functions. One we call getNumber+1, and the second we call getNumber+2. And notice that each of these two functions gets an attribute which is called self. And that's really the way how things work in Python. And that's somewhat different than in other languages. So if you're used to working with classes in other languages, that might be a little bit confusing for you because it works differently in Python. So in Python, the way it works is that every function within a class, every bound function, automatically gets the self, which is a reference to the instance that you currently work with, as the first argument of each function of that class. So you can see later in this example, when we call a.getNumber+1, you can see that we call it without any arguments. But what Python really does, it takes a itself, the instance that this function is called on, and it automatically puts it as the first argument within the function. So even though we don't explicitly put a as an argument, implicitly that's what happens. And a becomes the first argument, and it's the convention to call it self. And now in the function body, we can actually do things with self. We can access its members or attributes. And when we do self.x, we get a reference to the member x of this class. And we can work with it. So in this example, again, we instantiate a new instance of this class. And we set its x member to be 7. And now when we call getNumber+1, then self.x is 7, and +1 it's 8. And +2, likewise, will give us 9. And you can see that it actually works. But then again, that's actually not the recommended way to work with classes. Because what might happen is now I can create a new class. And then I try to call one of these functions. And again, I get this attribute error saying that this object has no attribute x. Because in the previous example, I explicitly set this value, and here I didn't do it. I forgot for some reason. And now it doesn't have the x attributes. So when you create a class, it's actually not a good idea to count on the user, which most of the time will be yourself, to actually to actually remember to set the right attributes. You just want the class to be created, and then you want it to be valid and already something you can actually work with. For that, we have in object-oriented programming the thing which is called a constructor, which is a very useful concept, which is some kind of special function. You can see it because it begins and ends with two underscores. And in Python, the constructor is defined by defining a function which is called underscore underscore init underscore underscore. So that's like a special function that Python knows to recognize. And that's the function that is called the first time that you create your class. So in the previous example, we didn't create a constructor. So when instantiating a new instance, we use empty parentheses. But now that we have a constructor, we, on top of the self, again, which is always an argument, we also add an argument x, which is expected to be received. And that's why here, when we create an instance of my class, we are forced to provide some argument, in this case, 7. Okay, and if we don't give 7, we'll get an error right at the time of creating this class. And then within the constructor, what we do is self.x equals x. Okay, so we take x and we put it as a member within the instance of this class. And that again illustrates the fact that a member is not like other variables. So self.x and x are not the same variable, okay? So x is the variable that we receive, and self.x is the member of this type. So it's important to always do self.x and not x, because, for example, here, self.x is not even defined. Yeah, question?
Can I take you back a bit again? Self-pointing, let's start. The self-pointing is what again?
OK, so when we do self.x here, that's actually a reference to a member of this instance, which is called an x. And this x, it's not a member. That's like the argument that we get in the function. So that's not the same thing. For example, here in this second function, if we just did x, it wouldn't work. It wouldn't know what x is. So because here we don't have an argument named x. So we need to do self.x. OK, and you can also see that here now we also added another argument to the getNumberPlus value, which is by default 1. So when we call it without arguments, then we just get 1 as default, which gives us 8. And when we use an argument 5, then we get 12. Yeah, questions?
Is there a way that, like, I want to know which attributes I have for this class? So I will say before the constructor, like I have x, I have y, I have length, whatever.
Yeah, so before the constructor, you don't have any members. So the first time that you have actually the opportunity to create members is within the constructor. But once it's created and instantiated, then you can actually see what members it has. We've already seen it. We have the dir function, okay, that given some object will tell us what attributes it has, including all the different functions and the different members. So we can see everything that is bound to this instance. OK. And like I said, adding the self to each function of a class can be sometimes non-intuitive, and people tend to forget that. So a very common mistake that people do is forgetting to add it. And then you get this strange-looking error that is sometimes a little bit difficult to understand what's going on. So you see that here we define a function, do something that gets a value. We create an instance of the class, and we call do something with the value 3. So it seems like everything is in place. We have a function do something that gets one argument, and we give it one argument. But for some reason, it gives us this type error saying that do something takes one position argument, but only 2 were given. But 2 were given. So you might ask yourself, why do you say that 2 were given? I just gave 1. But then you need to remember that every time that you call a bound function, the instance itself will be the first argument. So actually, it will be called do something, a, and then 3. Okay, so it might be confusing, but it's important to remember that. And we actually need to add the reference to self, even if we don't intend to use it. So you see that in this example, the function doesn't even need to use self. Still, we need to provide it. Questions? OK, so let's see a more concrete example of what it might be good for. So in this example, we create a class for DNA sequences. And this is very much in the spirit of the classes that we have in BioPython. So in BioPython, they already defined the sec class. And by the way, if you actually go to the BioPython source code and look at the code, you'll see very much in the spirit of what you see here. You see that they actually define classes for all the different types that they have. So that they have a sec and they have a sec record. And you see that each of those is just a Python class with all of those members and functions. OK, so let's try to make like a simple version of that. So we create a class. We call it DNASec. Within the constructor, we want to get the underlying sequence, which is expected to be some string. And automatically, we want to convert it into uppercase. We don't want to deal with the case of the letters. And we store it into the sec member of this instance. And then we add 2 functions. We add the isValid function, which validates that we only have A, C, G, and T nucleotides. The way we do that is we take the sequence and convert it to a set to get the unique set of letters used within this string. And we want to see that it's a subset of only A, C, G, and T. So if we have anything other than those 4 letters, we will get false. Okay? And then we also add a transcribe function that simply replaces the T to U and returns the RNA string. And you can see that we can use it. We define a DNA sequence with an invalid B letter, and you see that it's not valid. Or we can define a valid DNA sequence, and you see that it is valid, and we can transcribe it and get the RNA string. OK? OK, so let's elaborate on that. So here now we also create an RNA-seq class. So you can see that here we actually validate the sequence right when we construct it. So in this example, it won't even allow us to construct something that is invalid. You see that we create this underscore validate function, and we assert to make sure that it really holds, that that we only have the allowed letters, and if not, we get this error. And by the way, what you see here is called a class member. So you see that within a class, I define a member. It's not really a member. It's a variable named valid letters, which is called a class member. Now, that's not a member of instances. It's actually a member of the class itself. OK, so to access that, I actually need to write the name of the class and then access the variables. OK, so that's not global variables, and it's not members of an instance. It's actually a member of the class itself. It's something that stays constant for each of the instances of this class. Each of them will have the same valid letters variable.
Could it be changed?
Sorry?
Could it be changed?
Yeah, you can. Yeah,
We wouldn't
you wouldn't want to do it, but yeah, Python allows you to do everything. So.
change it changes for all the
Yeah, because it's a class member, then if you change it, it will change throughout the code for all of the members. Yeah. So yeah, so that's the class for DNASec, and then for RNASec, we do pretty much the same, just with the relevant adjustments. And also, like when we define the transcribe function here within DNASec, you see that now we actually return an RNASec object. And when we call the back transcribe function within RNASec, we get a DNASec object. Okay, so we can get access from one to the other and go back and forth. Okay, and you can see here that it works. We construct a DNA sec, and we transcribe it into an RNA sec, and we can print the underlying sequence. And you see that the underlying sequence of the DNA sec is actually the same as going then to the RNA sec and then back transcribe it back to DNA, and we get the original sequence like we expect. Okay, questions? Okay, now you see that this example actually works and it's very nice, but from programming perspective, there is something a little bit disturbing here. We have quite a lot of code duplication actually. So you can see that the DNA sec and the RNA sec are very similar, only with mild adjustments between one to the other. But mostly it's copy pasting of the code. And again, something we said multiple times throughout the course, that code duplication generally is not a good idea. So it creates codes that is harder to maintain and to debug. And we actually want everything to be written just once. For that, we have something that is called inheritance that allows us to create classes which are quite similar and have the same general patterns, only with some concrete and specific adjustments. So let's begin with the toy example first. So let's say that we create a class. We call it a base class, which has 3 functions. We have f1 and f2, which just give numbers. And then we have f3 that uses f1 and f2 to do something itself. Now what we can do, we can create what is called a subclass of the original superclass. And that is what is called inheritance. So we create a subclass that inherits from the base class. And the syntax is to use these parentheses that you see here. So we tell Python that we want subclass to be a subclass of the base class. And then within the subclass, we again define the f2 function. And that's what is called to override the function. So when subclass inherits from base class, what actually happens is that it inherits all of the functions which are defined in base class. So without explicitly writing them, subclass also has f1, f2, and f3. And unless we state otherwise, we get the same code that we have within base class. Only for f2, we explicitly override it and replace it with a different function that does something else. And now you can see that when we create this subclass, like I said, it already has f1, which is not overridden. So we get exactly what we had in the base class. f2 is overridden, so we get a new value, which is minus 66. And the most interesting thing happens when we call f3. So f3 was not overridden. It's still the same code of f1 plus f2. But because f2 was overridden, then we get a new value of f2. And you can see that we actually get 55 of the original f1 and minus 66 of the overridden function. And then f3 just gives us the sum of these two values. OK? Now, this concept of inheritance is actually very, very useful. For example, it's very common when we want to define our own custom exception types. So it's actually very. So we have this generic exception type, which is just called exception, and it's actually very common to inherit from that and create our own types of exceptions, which we can then use to define more nuanced kinds of errors that we want to deal with. For example, here we create a specific type of exception, which is called an invalid letters exception, which just inherits from exception, and it doesn't actually need to do anything, so it doesn't really have a body. And then, for example, we can define a validate DNA sec function that gets a DNA sequence, and if it's not valid, then we return an invalid letters exception with some message. And you see that we didn't actually have to write our own constructor for the exception because it already inherits the constructor of the exception type. So it already knows how to handle an error message like exception does.
Where is the exception defined?
Exception is a built-in type of Python. Okay, so it's something that just comes with Python. And actually all kinds of exceptions and errors inherit from exception. So you can see that now we can call this function, and if we give it something invalid that contains a B letter, then we will have this kind of specific exception type thrown, and we can actually catch it using the except statement like any other type of exception, and then handle that. And that's extremely useful because now we have a very concrete type of exception, and if we want, we can handle only this very specific type. If we used a generic type, for example, like a value error or something like that, then we couldn't be certain that what we catch is only the specific code that we intended to catch. But now that we have invented our own kind of exception type, then we can be quite certain that nobody else is throwing this exception at us. Only we can throw it because we are the ones to actually define it. OK, so that's one example where it can become handy to define our own types, which inherit from existing types. I should say as a side note that there is also this built-in type, which is called an object, which is some kind, we can think about it as like the archetype class that every other type in Python inherits from. So every time that we create a class, we actually implicitly inherit from the object type. And you can see it by using the isInstance function that given some object and some type will tell us whether this specific object is of the type of the specific class. So whether if we return true, whether this is the exact type or only a subtype. Okay, so unlike using the type function and then comparing to a specific type, which will only give true if that's exactly the type, isInstance is more flexible. It will tell us, it will give true, also if it's just a subclass that inherits from this type. And you can see that even though in the Python 3 version, we didn't inherit from the object, it's still an instance of an object. And in Python 2, it used to be the case that we had to explicitly inherit from objects. So sometimes if you see code that is Python 2 compatible, you can see that people use this to inherit from objects explicitly. But in Python, we don't need to do that anymore, and everything just inherits from objects. OK? OK, so back to our DNA and RNA-seq examples. So we began with this motivation we had that we saw we have a lot of code duplication between DNA-seq and RNA-seq, and we wanted to get rid of that. So one nice way to do that is to define a third class, which will be a superclass of these two subclasses. And the superclass will define all of the common and shared functionality, and then each of these two subclasses will only have to define the concrete differences and specific tweaks that we want within each of these two more specific types. So you can see that the generic sec class, again, it has a constructor which gets some string, it converts it to uppercase, and then validates it. And the way that the validation works is by making sure that the set of all letters that is used within the underlying string is a subset of another function which is called getValid letters, which in the superclass example is not even implemented. So if you try to instantiate a sec class, it wouldn't work for you because it would try to use the getValid letters function and then just throw a not implemented error, which is a standard type error that we use when we don't actually have an implementation in what is called sometimes an abstract class. So that's like a concept for classes which are actually not meant to be instantiated directly. We only want them to be used through specific subtypes which create all the needed functionality. So the sec class actually has missing functionality. So it doesn't have the getValid letters, and therefore you can't really use it. But now that we create some subclasses, DNA-seq and RNA-seq, you can see that each one of those it has the getValidLetters function, which gives concrete values. And now it's actually usable. Now it's actually something you can use because now you override this not implemented function with a function which is actually implemented. And then you can actually use these two classes. Okay, and for each of those, we also created transcribe and backtranscribe functions. Okay, and everything works like in the previous example, but without all of these code application. Questions? Okay, so that's pretty much all of the things I wanted to show you about how classes work in Python. I just want to end with a more practical example of a case where this can actually become quite handy. So the motivation we use is a code we had in lab exercise 3, if you remember. So there was this optional question of writing some code that given that could retrieve some sequence within, it was chromosome 11 in this case, but it doesn't really matter. So within a certain FASTA file, we want to retrieve a specific subsequence without reading the whole file. And if you remember, that required us to write quite complex code. So, by the way, if you want to run it, you need to download this FASTA file from this FTP site, and then you will also have to open the GZ compression. So you can use any software for uncompressing, like zip or RAR or 7-zip or anything like that. So I already downloaded it, and you can see that we can use the function we defined to actually read some sequence within chromosome 11. So we start with coordinate 100,500 all the way to 100,750. And we get 250 nucleotides that you see here. Now, like I said, the way it works is actually a little bit complex because we need to first determine two attributes of the FASTA file. So we need to see the length of the first line within the FASTA file, and then we need the length of all the other lines. And then if we want to convert coordinates within the chromosome to actual locations within the file, we need to take these two attributes into account and do this a little bit of annoying math that you see here. And only then we can actually read any arbitrary segment within a chromosome. But anyway, now that we do this, we get this nice function, and this actually works, and we can call this function as many times as we want. So it doesn't seem too bad. But if you look closely, you see that actually it's not a very good way to structure this code. And the main underlying problem is that we need to have these two variables. We need to have the header len and the line len, which these two functions are dependent on. And that's actually a bad sign. So if you see functions, global functions, which are dependent on some global variables, then this might give you a hint that this might be a good idea to refactor that and maybe turn it into a class which has its own members. And that might actually create problems if we now want to maybe handle more than one chromosome. So say we want to work both with chromosome 11 and chromosome 13. Then now if we do that, we are actually at a problem because each of them can theoretically have different header len and line len. And now we can no longer store them as just global variables because we would have this conflict between the two. And then it would actually become quite complex. We might find some solutions like maybe storing it in a dictionary or something like that, but this becomes quite cumbersome and not very easy to work in this way. So a good way to solve this problem is to actually use a class, okay? So what we can do, we can create this class, which is called a chromosome reader, that will have the header len and the line len stored as members. And then these two functions will be bound functions of this class. And now every time we can instantiate an instance of this class and actually work with a different chromosome reader. So you can see that the way we use it, we again open the file and we give the file handler to this type. And now that it gets the file handler, we get a valid chromosome reader that we can actually use. So we can now do CHR11 reader .readsec and give it 2 coordinates, and we can see that we can actually read the sequence that we have. And if we wanted to work with 3 different chromosomes, then it wouldn't be a problem. We could just instantiate 3 different chromosome readers, and each of them would have their own header len and line len, and we can work with them interchangeably without worrying that we would have all of those members mixed with one another. So the way we do that, we actually take all of these complex logic and we encapsulate all of it within one class. And now this class worries about everything. It has to worry about figuring out the coordinates and doing all of these conversions and everything else. Okay, so all the code that you see here is just put within this one class. But now that we do this, after we do that, we can actually forget about all of this code and have it completely compartmentalized within a class. And now we can just use it as a black box and not worrying about the specific implementation. And that, I think, is really the main motivation to work with classes and objects. So you can take any complex code that you work. You need to worry about writing it properly just once. But once you write it, you put it within a class, and then you can forget it for the rest of your life, at least until you maybe need to modify it or something. Whereas if you work with global variables and global functions, then actually you won't be able to forget about the details, because every time that you work with it, you will have to remember all the details and make sure that you have all the right variables and make sure not to override them. And this would create a much larger cognitive burden for you to actually maintain and work with this code. Okay, so the whole idea of working with classes is this capability of really compartmentalizing different sets of codes and forgetting about them. And now we can work with as many instances as we want without worrying about the underlying implementation. Okay, so I hope this gives some example of why this whole concept can be useful. And again, we didn't really go into this in too much details, like I said at the beginning. But I hope it gives you enough of an intuition of why this might be useful for. And I really encourage you to try to explore it and see if you can really use this to make your code easier to work with.